In this video, we will explore the various concepts associated with fluid dynamics. We will now examine flow rate. Flow rate is the product of the area of the tube the fluid is traveling through multiplied by the velocity of the fluid. We experimented with some different containers to see if we could calculate the velocity of the fluid by using several known quantities. Our first container was a half-liter bottle. Because we knew the total volume of the bottle, we were able to measure how long it took it to empty, and from that value we could calculate the flow rate. With a ruler, we were also able to measure the radius of the bottle's opening, which we then turned into an area. With the area in hand, we were able to divide the flow rate by the area in order to achieve the velocity of the fluid. In the case of the bottle, we found that the velocity of the fluid was 0.284 meters per second. We then performed the same experiment with the funnel and nozzle system. Again, we filled it with a half-liter of water and timed how long it took to empty. We then divided that value by the area of the nozzle in order to find the velocity of the fluid. In the case of the funnel, it was 1.25 meters per second. It makes sense that the fluid in the funnel is moving faster than the fluid in the bottle. The bottle has a larger opening and the funnel has a smaller opening. This means that the fluid in the funnel is forced through at a higher velocity, while the fluid in the bottle moves at a lower velocity. Another aspect of fluid dynamics is the density of a fluid. A fluid's density is defined as its mass over its volume. Everyone has experienced objects with different densities coming into contact with one another. Like when you throw a rock into the ocean. It's clear that the rock is denser than the water you throw it into, thus it sinks. In this video, you can see that we began by pouring water into the measuring cup, followed by vegetable oil. As you can see, the vegetable oil stays on top of the water, which means that it is less dense. To further back this point, we stirred the two liquids together. While it takes some time, you can see that the denser water sinks towards the bottom of the cup, while the less dense vegetable oil rises to the top. Now let us discuss some buoyancy force examples. A rectangular boat has sides of length 28 feet and 90 feet. When the boat is empty, it is submerged 5 feet into the water. Calculate the weight of the empty barge. If crates of grain are loaded onto the barge, it sinks to 7 feet below the water. For calculating the weight of the empty barge, it is necessary to use buoyancy force balance. We know that the force balance on an empty barge is buoyancy force minus the weight of the empty barge. This has to equal 0. This is because the force of buoyancy is an upward force, while the weight of the boat is a downward force due to gravity. These forces must equal 0 because the boat is static. Doing simple algebra, it can be concluded that the weight of the empty barge is equal to the buoyancy force. For this example, the buoyancy force can be summarized by the following equation: density of water multiplied by gravity multiplied by the volume of the barge that is submerged. We know that the specific weight of the fluid is equal to the density of the fluid multiplied by gravity. In this problem, the specific weight of water is given to be 62.4 pounds per foot cubed. Therefore, we know that the buoyancy force is now 62.4 pounds per foot cubed, multiplied by the submerged volume. The volume of the barge that is submerged is the width multiplied by the length, multiplied by the submerged distance. Therefore, the final equation for the buoyancy force is 62.4 pounds per foot cubed, multiplied by 28 feet, multiplied by 90 feet, multiplied by 5 feet. Doing the calculations for this yields a buoyancy force of 786,240 pounds. This solves our first question. which asks the weight of the empty barge. For the second question, we know that the total sum of all forces in the y direction must equal 0. Therefore, the buoyancy force due to the grain plus the buoyancy force due to the barge minus the weight of the empty barge minus the weight of the grain is equal to 0. After doing basic algebra, we know that the weight of the grain is equal to the buoyancy force due to the grain, which is equal to the specific weight of water multiplied by the change in submerged volume. This can be explained as 62.4 pounds per feet cubed multiplied by 28 feet multiplied by 90 feet multiplied by 2 feet, which yields a weight of 314,496 pounds.